Hello and welcome to the Unit 3 podcast on Section 8.4. Today we're going to talk about metallic bonding. I'm Mr. Sakaguchi,
And I'm Mr. Lin.
as usual, and let us start. So metallic bonds, they're not quite like ionic bonds, but they are related indirectly to them in the sense that they're special for metals. Now these are things that are made up of metals only, no non-metals present here. These are not ionic bonds. Metal atoms do form lattices just like ionic compounds do. However, there's no loss or gain of electrons.
And it's not anywhere near as rigid as the crystal lattice in an ionic compound.
What we find for metals is that their valence electrons are called free electrons, and they're kind of, the reason why they're called free is because they can move around and they're not really associated with a specific metallic atom. Sometimes it's referred to as the electron sea model because the electrons can kind of flow around like the way water flows around in oceans.
Right, so these electrons are called delocalized electrons because they're not restricted to any center or any specific metal ion.
So what we find is that the cationic core metallic atoms stays relatively fixed, and the valence electrons are kind of free to move around.
So the relationship to the ionic bonds is that it's still formed from the attraction between positive and negative charges.
Properties of these metals and metallic bonds. Melting points for metals will vary greatly depending upon the metal itself, so there is no easy trend to say high or low.
But they do have a tendency to have a lower melting point than ionic compounds, which have really high melting points.
True. Metals are malleable, they're ductile and durable. So malleable means that it can be pounded into thin sheets.
And ductile means you can stretch it out into wires.
And so when I say durable, I mean that metal upon impact doesn't shatter, it just bends.
So as a result of this, we make a lot of materials out of these, like ships, buildings, etc.
They're also good conductors of electricity, and given the electron sea model and the delocalized electrons, that kind of makes sense that electricity, which is essentially moving electrons, can flow through metals.
Right. So in particular in the case of transition metals, the inner or d electrons as well as the s electrons are able to flow around, and that's what gives them that good conductance.
And what we find is that as you have more delocalized electrons, the strength and hardness of these metals will tend to increase. We also have alloys of metals. These are mixtures of different metals. You've probably heard of this with respect to like buildings and like swords and junk like that. And they're mixtures of metal elements that enhance certain metallic properties.
Right. So iron is pretty strong material on its own, but if you mix it with something like carbon, which isn't even a metal, it makes it much stronger. Or your home kitchen utensil, like the stainless steel forks and spoons and knives, it's because you're mixing iron with chrome, and that makes it resistant to rusting. So a mixing of these different compounds gives metals new and unique properties, which we find really useful.
Now there are two different kinds of alloys to be aware of. There are substitutional alloys and there are interstitial alloys. Substitution alloys, you find that the metals that are being mixed together are approximately the same atomic size, so it's just mixed together throughout. So for instance, brass and pewter and 10-karat gold would be examples of common substitutional alloys. Interstitial alloys, there's a vast difference between the sizes of the metal atom versus the other atoms that are being mixed with it. Now it doesn't always have to be another metal that's mixed in with the metal. When there's big differences like this, what we find is that these smaller atoms will actually fit in the grooves in between the larger ones, and often we find this enhances the strength and rigidity of these metals. So for instance, carbon steel, which is used in buildings and the freeway and stuff like that, had different amounts of carbon mixed into it depending upon how much strength you want to give it or rigidity.
So let's say you wanted to like just stack bowling balls, for instance. You'd actually have a stronger structure of bowling balls stacked up if you put tennis balls in between them, and they'll actually hold together in that shape much more strongly than if those just bowling balls on their own. And that's how an interstitial alloy works.
And I believe that's it.
Oh, okay.
So until next time.